In this segment, let's take a look at the median. Now, we're talking about confidence intervals, and this is an extremely important concept. I believe I've mentioned this before. A confidence interval is always used to estimate a population parameter. It's a matter of you identifying which parameter is appropriate for whatever work you're doing or wherever the data leads you to, and it's about estimating the parameter value. It is absolutely never, ever is it about estimating a sample statistic. You know the sample statistic, you collected the data, you calculated it, you have a sample statistic. What you don't have is a parameter value. So you're trying to estimate the parameter value. Now, a confidence interval for the median is typically used when the assumptions for the mean can't be satisfied. The basic idea for means, you have data, you want to use a t-interval a t-distribution to construct your confidence interval. The central limit theorem won't apply because your sample size is too small. You take a look at a normal plot. It's not normal, so you really can't realistically talk about the mean. There'll definitely be some issues if you'd built a confidence interval for the mean based on non-normal data. So because of that, you'd switch to the median. Or there are times when the actual research requirements specify the median. Very commonly in medical research, the median is used much more than the mean is used. Oops, there we go. There we go. Now consider the following data, which consists of time in minutes, reported for pain medication to take effect, and estimate the true average time with a 95% certainty. What you want to do now is go ahead and pause the video for a moment and enter that data in your calculator so that we can work together with it. I have to put mine into L1. Obviously, you put yours wherever you want to, just make sure you know where it is. Now, we want to go ahead and estimate the true average. That's what we're starting off to do. Okay, so now we have the data. Let's take a look at the process. Well, the assumptions is that the population is distributed normal. That's the basic assumption that we're going to be working off of. Remember, I'm thinking mean here, the average all the way. So, how will I address that? Will the CLT apply? No, it won't. This sample size is only 15. We need at least 30 in order to feel comfortable. So what will we do next? A normal plot. So let's switch to the calculator and take a look. If I go to Program, Norm Plot, run the program, it's stored in a list, and I put my data in L1, that's what my normal plot looks like. And there's definitely issues with that. We need to do that again. Let's do that part again. Okay. So go to Program, Normal Plot, run the program. It's stored in a list. My data is in L1. Take a look at this, and there's definitely issues with it. If you look in the upper right-hand corner, there's two data points that are way out there. It looks like this data is heavily skewed right. And actually, if you look at those two data points and then compare it to the rest of the plot, if those two are eliminated, I'm willing to bet it would be extremely normal. It looked really good. But you can't just throw away data because it doesn't do what you want it to do. Now, that may be justification to identify those data points, go back to the records, and see if there's something very unusual going on that they really don't belong there. But this is what we have. This is not normal. So, what I would expect my students to do would be to give me a quick replica of the normal plot. For me, just enough that I know you actually looked at it. If I saw this, then I know, yeah, you really did the normal plot. Okay, this is definitely not normal. This is about as gross of a violation as you're going to get. Okay, so our assumption's been violated. We want to construct a confidence interval for mu, but we can't. So we're going to switch to the median, the physical center. Now your textbook presents two different cases. The first case is a large sample case and the other is a small sample case. I'm going to present here only the small sample case. The reason being from personal philosophy is a small sample case always works. if I use a small sample case on larger data, then that's fine. It's going to work just fine. Now, they won't agree. The small sample case and large sample case will not agree until the sample size gets very large. But keep in mind, the confidence intervals are not exact. The mathematics are exact. The actual intervals are not. So that's what we're going to do here. I'm going to walk you through the small sample case. Now, let's go talk just a moment. Let's suppose that we did a confidence interval for the mean, mu, based on the normal distribution. If we did a 95% confidence interval, the idea is that we're going to find this value here and here such that it encompasses 95% of all of my data. If I look at this from a cumulative point of view, if I start from the end and I work to the right, I'm accumulating area under the curve such that at this point I have 0.025. When I get all the way over to here, this point, I have 0.975. That's my 0.95 plus my 0.025 when I actually make it to this point. And of course, all the way over to the right, and technically you go to infinity, you have 1. All of the probabilities. Well, I'm going to approach the confidence interval for the median with the same basic idea. I'm going to base it on a binomial. With a binomial, you could have 0 successes, 1 success, 2 successes, 3 successes, 4. In this particular case, up to maybe 11, 12, 13, 14, and 15, because n was 15. So you could have all successes, no successes, and everything in between. Well, if I start thinking in terms of binomial, cumulative distribution, if I take the probability of no successes plus the probability of 1 success and keep going probability of 2 successes, if I keep going, at some point I should hit a probability of about 0.025. And when I do, let's just say that it happens at 2 successes. And I don't know, I haven't done this yet, we'll find out in a minute. But if it happened at 2 successes, then I would say, all right, it's the second observation. That's how far I'm going to go. I'm going to identify the second observation of my data and say that's the lower bound for my confidence interval. And I keep adding up, and let's just suppose it happened again at, say, the 13th. By again, I mean I have this 0.975 that I'm looking for. See, I'm adding up the probability as I go along. As I'm going this direction, I'm accumulating all those probabilities. Well, if that happened at the 13th position, then I would go to the 13th position of my data and say, all right, that's what I'm going to use for the upper bound of my confidence interval. So I'll be roughly 95% certain that theta, the true median, is somewhere between my 2nd and 13th. But of course, I replace the 2nd and 13th with the actual data values, which means I need to sort the data. So what's the process going to be? Well, first of all, in my calculator, I'm going to enter 0, 1, 2, 3, 4, all the way down to 15. And then in another list, I'm going to actually put my data. Then in another list, I'm going to use binom CDF. Now there's 15 here, 15 observations, so n's going to be 15. This is based on the median. Think in terms of if I reach in the data, what's the probability I get a value below the median? It's a half. It stays constant for all the trials, so that's why it fits the binomial. So I'm going to say pi is a half. And then x. X is my number of successes. Well, if this is L1, this is L2, and this is L3, then I'm going to tell it L1. So it's going to go over here and say, all right, 0. Find the probability of 0 or fewer, which is just 0. Then go to here and say, okay, what's the probability of 1 or fewer? That's 0 and 1, and put that value here. 2, that's CDF from 0 to 2, put the value here. It's going to calculate all these probabilities. So going down the list would be like going left to right on this diagram. Then if my data is sorted, if I saw at 2, if I saw 0.025, then that's saying I need to go to the second data value, whatever data value happens to be sitting right there. And likewise, as I continue down here at some point, 0.975, and then there's my data value. That's the one I'm going to be working with. All right, now, because this is discrete data, the probability of you hitting actually 0.025 and 0.975 is about nil. It's not going to happen. So, if I go inside, if I go into here, if I pick a value into here, say at this point, see this probability is going to be bigger than 0.025. If I pick a value in here, this probability is going to be, on this side, is going to be bigger than 0.025. That means if I want a 95% confidence interval, I'm going to have something less than 95% confidence interval. So my approach is going to be, I'm going to go to the value that gives me 0.025 or as close to, but not going over as I can. So it's probably going to be slightly less. Over here at the 0.97 mark, it's probably going to be slightly more. That means in my tails, I'm going to have slightly less combined, slightly less than 0.05, which is what I'd want for my 95% confidence interval. Well, all I'm doing is I'm acknowledging the fact that it's discrete. I'm not going to get exactly 95, but I asked for a 95, so my approach is going to be at least a 95. So I may end up with a 95.6 or 96.2 or something like that. All right, let's go ahead and switch to the calculator. And there's my data. Matter of fact, I'm going to copy my data. Just type L1 here. I just copy my data into L2. And over here in L1, I'm going to go up to it and clear it out. And I'm going to put in my 0, 1, 2, 3, 4. 0 through 15. Whoops. Actually, I don't need the 0. I'm going to delete the 0. The probability to be calculated, but really it's my first position, second position, so I don't actually need the 0 there when I enter my calculator. If I go back to Stat, Option 2, Sort Ascending, I'm going to sort L2. Done. Go back to the editor. See, now the calculator shows my lowest value up to my highest values. Now I'm going to we'll go up to L3. Go to Second Distribution, Binom CDF. Remember, n was 15. Pi is a half. And my x's are in L1. Hit Enter. And give it a second. There's my probabilities. Remember, I'm looking for 0.025. So this is going top to bottom. It's like going left to right on that diagram I drew. Well, 0.025 falls somewhere in between these guys. So, with the idea of making at least a 95% confidence interval, I'm going to go here to 0.0176. And right there is the left end of my confidence interval. So I'm going to write that down so I don't forget it. I know the left end is going to be 13.2. And you can see 13.2, that's going to give me a value out here, kind of like this green one I did. It's not quite at 0.025. So now let's go back to the calculator and look for the other end. So I'm going to slide down here, and I'm looking for 0.975. Well, it's not there, obviously, but 0.94, 0.98, it's in between these two. Again, I'm going to go to the outside to make sure I have at least a 95% confidence interval. And 18.1 is my value. Okay, so I'm going to write that down. 18.1. So there's my confidence interval. I could say this is an approximately a 95% confidence interval for, what's the parameter? Theta. Now, I can actually do a little bit better than that because I know on the lower end when I did it, this probability here was actually 0.0176. And on the upper end was, what was it, 0.9824. So what I can do is notice the left tail is actually equal to the right tail. If you take 1 minus 0.9824, you get 0.0176. So that means that alpha is actually equal to twice 0.0176, which is 0.0352. We wanted this to be 5%, 0.05, but because of the discreteness of the data, just couldn't do it. So if I take 1 minus alpha, .9648. I wanted a 95% confidence interval. I actually got about a 96.48% confidence interval. Fix that. 96.48% confidence interval. So now I can be a little bit more accurate and say I'm about 96% certain that the true population median, whatever the value is going to be somewhere between 13.2 and 18.1 minutes. Okay, that's all there is to it. It uses some prior knowledge. It uses the binomial distribution. It uses the idea of cumulative probabilities. That's really all there is to it. Like I said earlier, you can take a look in the book if you want and look at the large sample case. Talk to your professor and see what your professor prefers you to do. And that's it for this section.